30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds.
I believe that this nation should commit itself.
12, 11, 10, 9. Ignition sequence start.
To achieving the goal
5,
before this decade is out.
2, 1. Liftoff. We have a liftoff.
Of landing a man on the moon and returning him safely to the Earth.
Liftoff, the clock's running.
On July 20th, 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first men to set foot upon the moon.
Houston, the Eagle has landed. That's one small step for man, one giant leap for mankind.
4 months later, Apollo 12 successfully landed on the lunar surface, and astronauts Peter Conrad and Al Bean walked on the moon November 19, 1969. And in April 1970, NASA launched the crew of Apollo 13 into the vast ocean of space to continue man's lunar exploration. But 56 hours into the mission, a devastating malfunction left the spacecraft leaking precious oxygen and the crew of 3 astronauts facing a life and death crisis.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
We could have lost O2 tank 2. We got to get a pressure readout on that thing.
O2 quantity number 2 is 0.
We are vetting something out into space.
Apollo 13's mission priority was no longer lunar exploration, but survival. With ground teams working around the clock, NASA faced the formidable task of returning the crew safely to the Earth.
Failure of the oxygen tank on Apollo 13 almost brought the mission to an end in a catastrophic way.
The mood in mission control was immediately one of disbelief.
I have absolutely no clue to what happened. Something happened to the fuel cells in the oxygen tank.
We're going to hit 100 psi in an hour and 54 minutes. That's the end right there.
So they only had a few minutes of power left.
We're still 70 to 80 hours away from the Earth.
We were running out of time to get the spacecraft back on course.
I don't think we should ever believe that rescue was inevitable here.
Without use of the lunar module, the mission was lost.
What do you think we got in the spacecraft that's good? It looks grim.
This 2-part film will tell the story of the men, the mission, and 13 remarkable factors that cemented Apollo 13's safe return to Earth as NASA's finest hour.
I'd say this is as serious a situation as we have ever had in manned spaceflight.
Previously in Part 1.
When I looked up and saw both oxygen pressures, one absolutely 0 and the other one going down, it dawned on me that we were indeed in serious trouble.
After a ruptured oxygen tank cripples the Apollo 13 spacecraft, mission control and the astronauts immediately follow emergency procedures.
The only way to survive the situation was to transfer to the lunar module.
The lunar module could act as a lifeboat because it's an independent spacecraft. They were able to use it as a backup to the failed systems in the command module.
It normally took 5 hours to power up a lunar module. They had to do it in 90 minutes.
Without knowing exactly which way the spacecraft is in space, there's no way to get back home again.
Alignment was normally done using stars. The problem after the incident was that there was debris floating around the spacecraft.
The lunar module's descent engine is fired to put the spacecraft on a return trajectory back to Earth.
Okay, Aquarius, you're looking good.
Okay, Houston, burn complete.
NASA works to reconfigure the 2-man lunar module to keep 3 men alive for over 90 hours.
One of the great triumphs of the Apollo 13 rescue was the way in which the team managed to eke out the consumable store.
In a situation like that, there's only one thing you can do. You just keep going, and you just keep thinking up where you can get more consumables.
We've had loss of signal with Apollo 13 as it passes above the backside of the moon. We're at 77 hours, 9 minutes, standing by, continuing to monitor. This is Apollo Control, Houston. Apollo Control, Houston. We're coming up now on 1 minute from time of reacquiring Apollo 13. Standing by now for acquisition.
Aquarius Houston, over. Aquarius Houston, over. Apollo 13, Houston.
Go ahead, Houston.
Hey, you're loud and clear now.
Roger.
With the lunar module acting as a lifeboat and the spacecraft back on the free return trajectory, Apollo 13 is on course to splash down in the Indian Ocean in 4 days' time. But with no recovery forces deployed in the Indian Ocean, the crew would be left floating in the command module waiting for rescue. Mission Control must reduce the flight time to have splashdown in the Pacific Ocean, where naval recovery forces are already in waiting.
Our first milestone was to get us back on free return. The second one was to get us home early. The flight time back home was 155 hours if we had done nothing else. But the ground had decided to burn at about 2 hours past the moon, at about 79 hours, a maneuver to shorten the time to get home again.
Not only will a shorter flight time put less strain on the consumables, but it will also ensure the capsule re-enters the Earth's atmosphere above the Pacific Ocean. The team at Mission Control have two burn options. Both will require the use of the lunar module's descent engine. The first will speed up the flight by 36 hours. Although the fastest of the two options, this burn will require jettisoning the service module, something NASA is reluctant to do.
That would expose the heat shield of the command module to very high and very low temperatures, and they were very concerned about cracking that. I mean, that heat shield was absolutely the lifeline. You couldn't re-enter the Earth's atmosphere if that wasn't in a good condition.
The main heat shield, of course, was not designed to operate in free space for extended periods of time. It's designed for re-entering the Earth. And there was some concern if you jettisoned the service module that you'd cold soak that heat shield and get problems, so for that reason they preferred to keep the service module on.
Nobody knew if the command module could survive that thermal condition, super cold temperatures of space, coming back all the way without the service module attached.
And in addition, the burn will require all remaining fuel for the engine, posing yet another problem.
Further corrections to the spacecraft trajectory that may be necessary as the spacecraft approached Earth would no longer be possible.
With this in mind, NASA chooses the safer second option, a shorter 4-minute burn that will return the crew only 12 hours sooner, but will preserve fuel for later course corrections.
Given the success that the mission operations team were having in stretching out the amount of time that the consumables would last, there was no necessity to go for these very extreme options, and they could afford, therefore, to take the lower energy approach, leave some fuel in reserve, keep the heat shield safe, and come back at about launch plus 142 hours.
It was mainly a question of what is the safest way to do this. And all the decisions that were made turned out to be exactly right, because they came back almost the slowest routes you could from the moon, because they wanted to retain the possibility of making some small corrections between the moon and getting back to the Earth, so that they came in just the right height in the atmosphere. And as they approached the Earth, actually, they started drifting away, and they were quite anxious about that. So having preserved some fuel in the LEM motor for doing these corrections was exactly the right decision, because they actually needed to make those corrections on their way to Earth. It would have been horrifying if they'd, saved the astronauts only to see them zoom past the Earth, by a few miles, or crunch into the atmosphere and get burnt up, both of which were possibilities.
The precision of this burn is so critical that the flight dynamics team at Mission Control insist that the lunar module's guidance computer be used to control the spacecraft. But as this system drains a lot of power, it will have to be permanently shut down once the burn is complete. From then on, the astronauts will be flying manually.
The descent propulsion system burn duration 4 minutes 24 seconds. Flight Director Gene Kranz now going around the room for a go, no-go status from each member of his team.
Aquarius, Houston, over.
Go ahead, Houston.
Jim, you are go for the burn. Go for the burn.
Roger, understand. Go for the burn.
Less than 30 seconds away from scheduled time of ignition on our Parasynthian plus 2-hour burn for the Apollo 13. The engine is armed, standing by.
We're burning 40%.
Aquarius, Houston, you're looking good.
Roger.
Go with 2 minutes.
2 minutes, Roger.
Go with 3 minutes. 10 seconds to go.
Shut down.
Roger, shut down. I say that was a good burn.
Roger. So now we want to power down as soon as possible.
Commander Jim Lovell reporting shutdown. The engine is off. Apollo 13 now 5,426 nautical miles out from the moon. We're at 79 hours, 32 minutes into the flight.
Almost exactly 24 hours after the oxygen tank rupture, the crew complete the burn. Apollo 13 will now arrive back at Earth for a splashdown in the Pacific. But in order to preserve consumables, every system in the lunar module is once again powered down, except for the guidance, communications, and water cooling systems.
The ground was very much concerned with power, and we were too. And we decided to go into a power down mode. We turned off just about everything.
I guess everybody, myself included, got a little bit fooled about how low the LEM actually could get down to, and after completing this power down, it settled down on consuming about 11 amps an hour.
The lunar module, one of the most sophisticated machines ever built, is now running on less power than a household vacuum cleaner.
This is Apollo Control at 82 hours 30 minutes. The lunar module has been powered down. On board the spacecraft, all 3 crewmen are scheduled to be eating at this time.
In a strange way, the uniqueness of Apollo 13 came to our aid again, because this was the first mission to carry actually a level of wet pack food. So being unable to use drinking water because water was so scarce, they could actually suck moisture out of the wet pack foods to get water and electrolytes, which the body desperately needs in order to maintain the mental faculties. And mental faculties were needed pretty sharp for the crew under those appalling conditions.
With Apollo 13 speeding back towards the Earth, the crew can at last afford to catch up on some much-needed sleep.
Of course, in the early periods of this particular flight, we didn't want to sleep too much. We were sort of worried of what was going to go on. But I went into the command module one time to go to sleep, and Jack was on top of the couch, and I said, "Jack, put up all the window shades. Let's get the place nice and dark. We'll just relax and have it nice and dark in here. We can really get some sleep." And I woke up a couple hours later, and I was freezing. As normally happens, putting up window shades in space cuts out the sunlight and normally cools down the spacecraft, but in most flights, the heat from the systems will quickly re-warm it, and as soon as we get the window shades up, you'll be in normal position again. But we got the window shades off after that, and the spacecraft never did warm up again. Command module just slowly kept going down in temperature until I think just prior to re-entry, down to about 38 degrees.
With no power for the electric heating, temperatures inside the spacecraft drop to almost freezing point.
How does it feel, Jack?
I tell you, it gets cold. I don't know whether we'll be able to sleep tonight. It must be about 35 or 40 degrees. And they both came down here rubbing their hands, shivering. It's pretty cool upstairs.
Right, that's what I was worried about.
The command module, which was dead, completely switched off, completely lifeless, was cold. There was ice forming on the inside of the windows. The crew were beginning to suffer because of that environment.
We became concerned about keeping warm, and Fred and I broke out our lunar boots, which we had stowed away in the lunar module, and Jack looked at his wet feet a couple times. But he had an extra set of underwear, so he put that on.
They were so cold, they were not even able to sleep properly. And in restricting their water intake, I think Fred Haise had a urinary problem as a consequence, and he was in pain for quite a lot of time on the way back.
It was sort of a chilling coldness. The walls were perspiring, the windows were completely wet, and it wasn't too healthy. I recall that we went in there to get some hot dogs one day, and it was like reaching into the freezer for the food.
It was a dire state. It was a real emergency situation.
The dropping temperatures not only pose a threat to the astronauts, but to vital equipment on board the spacecraft, which can be damaged by the extreme cold.
In normal flight, the command service module would maintain reasonably steady temperatures. So you design things generally to work about 20 degrees centigrade, you know, normal temperature. And you don't want things going too far away from that.
With the crew and the success of the mission dependent on this precision equipment, it is essential that Mission Control keep the spacecraft within the acceptable thermal conditions.
The people here in Mission Control Center are looking at ways of setting up passive thermal control for thermal balance for the spacecraft during the remainder of the coasting flight.
As well as facing the freezing temperatures of deep space, one side of the spacecraft is constantly baked by the extreme heat of the sun.
In Earth orbit, of course, low Earth orbit at least, half the time you're in sunlight, half the time you're in darkness. On the way to the moon, the sun's there all the time. So you don't want one side of the spacecraft getting hot and the other side getting very cold.
Mission Control instructs the crew to initiate passive thermal control, a maneuver that slowly rotates the spacecraft to evenly distribute the sun's intense heat.
Okay, Jim, in order to maintain even heating, we just have to yaw the whole machine about 90 degrees.
Okay, we have to yaw the machine and take them at the 90 degrees.
That's affirmed.
So they use passive thermal control barbecue mode, which is rotating the thing about three rotations an hour to stabilize the temperature. And it also sort of controls the attitude of the thing, a bit like a rifle bullet, so it doesn't drift off too much.
This passive thermal control procedure had been used on other Apollo missions to ensure the spacecraft was kept at an optimum operating temperature. But for Apollo 13, the maneuver has the added bonus of warming the crew in the near-freezing lunar module.
They modified the angle of the spacecraft so that the sun would warm up. They warmed them up through the windows, basically.
Mission Control and the crew have been successful in establishing passive thermal control, but there is little time for celebration. Ground teams must now turn their attention to a new problem looming on board the spacecraft.
When you breathe oxygen, you exhale carbon dioxide. And that carbon dioxide, if you don't do anything about it, builds up in the sealed environment of the space capsule and becomes a poison. And so, left unchecked, the carbon dioxide concentration goes up, the astronauts feel sleepier and sleepier, and eventually they go to sleep and never wake up.
However, all of the Apollo spacecraft have systems that can remove carbon dioxide from the air in a process known as scrubbing.
You blow the air through crystals of something called lithium hydroxide, and there's a chemical reaction, and it captures into a solid form the carbon dioxide, takes it out of the air, and then you get fresh air coming out the other side. The command module had a scrubbing system, so did the lunar module, but the lunar module was designed to carry 2 men for 2 days, whereas now it had to carry 3 men for 4 days. So that's 3 times longer, 3 times more carbon dioxide being exhaled by these men.
With this additional carbon dioxide, the scrubbing canisters in the lunar module are being overwhelmed. However, the command module has plenty of unused canisters. But with the command module powered down, its scrubbing systems are not operational.
It wasn't possible to take the lithium hydroxide crystals from the command module and place them in the lunar module because the shapes were different.
Because two manufacturers had bid and competed for these two separate spacecraft, and they each built their own design of lithium hydroxide canister.
The command module canisters of lithium hydroxide were square cross-section, and believe it or not, the ones in the LEM were round cross-section. So you couldn't take a canister from the command module and just plug it into the slot in the LEM.
So the problem that the mission controllers faced and the astronauts faced was how to make a square peg fit a round hole.
This was a very serious problem. I mean, it could easily have been the end of the rescue mission had they not solved it.
NASA engineers must rapidly devise a system that converts the square command module canisters for use in the lunar module before the carbon dioxide reaches dangerous levels.
Okay, just some info. We're working up a procedure for you to use command module LiOH canisters in the LEM so that you can continue scrubbing the LEM atmosphere. So sometime in the future we'll be coming up to you with that procedure.
A group of life support engineers at NASA knew immediately after the oxygen tank rupture that if the lunar module was used as a lifeboat, then carbon dioxide poisoning was going to be a problem. They also knew the astronauts would somehow need to patch command module canisters into the lunar module's life support system if the crew were to make it home alive. The responsibility fell on this team of engineers to construct a canister adapter using only equipment available to the astronauts on board the spacecraft before CO2 levels get dangerously high.
The guys said, okay, lay out on the table what we've got, and let's get a lunar module canister and a command module canister. How do we bring these together?
Here again, I think we must pay credit to NASA for its incredibly philosophically intelligent way of organizing missions. Everything that went on the spacecraft went onto an inventory. So the people on the ground knew everything that was on the spacecraft, and that gave them the opportunity to sort of assemble all of this in their minds and say, hey, what have we got up there? What can we actually put together to overcome this problem?
Within hours, the team have created an adapter using spacesuit hoses, plastic bags, and cardboard flight plans. But holding all of these components together to create the vital airtight seal is one of NASA's secret weapons.
Duct tape. We couldn't have gone to the moon without duct tape, and we certainly wouldn't have got the Apollo 13 crew back without duct tape. It was very, very useful.
If you're in a weightless environment and you want to stop your pencil kind of just wandering off into somewhere else, you stick it to the wall with a piece of duct tape. You're forever sticking up lists of instructions or lists of things to do or pieces of equipment to the walls with duct tape. And clever minds might think of a way of getting around it if you didn't have duct tape, but it was the obvious thing to use, and luckily they had some there. But I use the word luckily, I mean, it was because it was a useful thing to have, and they had it on board.
This is the scavenging hose, the exhaust hose, if you will, from the suit. And we just put the lithium hydroxide canister on the end of it, and it's not so easy to fasten on there.
They placed the rectangular lithium hydroxide canister inside the plastic bag with a hole in front of the astronaut's spacesuit pipe that then allowed air to be pushed through that lithium hydroxide canister.
We've used a data card out of the flight plan to make a structure so that the plastic cover here won't collapse on the end of the hose.
And they then found a way of connecting at the other end of the spacesuit hose to a spent lithium hydroxide canister already fitted in the lunar module.
And we've had one of these running for about 3 hours over in the 11-foot chamber in Crew Systems, and all indications are that it's doing the job.
So it literally was cobbled together on a desktop. It sounds Heath Robinson, but in fact it was just make, do and mend. And that's often the best way for solutions.
Mission Control's final hurdle is creating a clear procedure for the tired and cold astronauts to follow to correctly assemble the canister adapter.
We wish we could send you a kit, and it'd be kind of like putting a model airplane together or something. As it turns out, this contraption will look like a mailbox when you get it all put together.
The ground read us up a procedure in order to adapt some of the command module lithium hydroxide canisters for use in the LEM. And as they read this thing up, Jim and I constructed one of these things.
Cut a piece of tape this long, put it up there, do this, do that. So the guys in the LEM actually replicated this, and it worked a treat. You know, within an hour of switching it on, the carbon dioxide levels were way down, and they were through that really serious consumable problem.
So these were very effective devices, and we used 4 of these command module canisters and never did use the main canister that we had in reserve for the LEM.
We're now showing 0.1 partial pressure of carbon dioxide in the lunar module. So apparently the engineering using the command module lithium hydroxide canisters and the plastic bag and the suit hoses is working out all right. And at 96 hours, 3 minutes ground elapsed time, this is Apollo Control, standing by.
Having avoided carbon dioxide poisoning, the crew can breathe easy. But concerns are now growing at Mission Control about the spacecraft's trajectory. The flight dynamics team tracking Apollo 13 can see it drifting off course. Although this drift is small, its impact on the capsule's re-entry into the Earth's atmosphere could be disastrous.
You are looking to enter the Earth's atmosphere around the side of this great big sphere at an angle of between just 5.5 and 7.5 degrees, coming all the way back from the Moon. So the precision with which you align the flight path is crucial to keeping the crew alive.
If Apollo 13 stays on this drifting flight path, its re-entry angle will be too shallow, and the capsule will skim off the Earth's atmosphere, stranding the crew in space. The astronauts must once again perform a precision burn of the lunar module's descent propulsion system and trim their flight path, steepening the capsule's re-entry angle, ensuring it is captured by the Earth's atmosphere. But if the burn is not accurate and the angle is made too steep, the heat shield on the capsule will fail and the crew will burn up during re-entry. The astronauts' lives now depend on the accuracy of this maneuver, but with no power to run the lunar module's primary guidance computer, it was shut down after the last acceleration burn. Mission Control now need a method to precisely align the spacecraft to have any chance of correcting the re-entry angle.
The procedure for putting the spacecraft in the proper attitude would be to use the Sun and the Earth as reference points. This, of course, would be a backup procedure. The normal procedure would be to use the onboard guidance equipment, and only in the event of some unforeseen failure would this backup procedure be used.
With no power available for the lunar module's primary guidance system, the crew must use the secondary abort guidance system, which consumes less power. This system will help the crew position the spacecraft for an accurate burn, but must first be calibrated to be of any use. The technique that must now be used has only ever been trialled once before, by only one astronaut, Jim Lovell.
On Apollo 8, we were concerned with perhaps losing a platform on the return voyage home, and since no one had ever made a lunar trip before, we were looking at sort of way out ways of determining how we could make these corrections home. And some of our people here at MSC had come up with an idea about using the terminator of the Earth to orient the spacecraft and then the sun position to get orientation and pitch. And with that knowledge, we could then make corrections to correct our angle of entry into the atmosphere.
This backup procedure uses the Earth's terminator as a target. The terminator line is the separation between the illuminated day side and dark night side of the planet. The terminator provides a fixed target on the Earth and can be used to establish an accurate alignment.
And the way that they did this was to use the Crewman Optical Alignment System, or COAS. And by maneuvering the spacecraft so that the COAS had the Earth's terminator aligned with the site, it was possible to create the correct geometry for the burn to take place in the right direction.
So at 105 hours, they gave us instructions to relight the descent engine, to orient the spacecraft in this manner, and give this particular procedure a try. And when they read up the procedure to us, I just couldn't believe it, because even on Apollo 8, I thought I'd never in all the world have to use something way out as this. And here I was on Apollo 13 using this very same procedure that was developed some time ago.
Okay, Jim, now basically if you put the horizontal line on the COAS on the horns of the Earth, that will put us in burn attitude.
Okay, I think I have a handle on the attitude, the way the Earth should look at the COAS.
Thank you.
And thank you.
This was a really complex problem because without the benefit of automated systems, it was a three-man job.
Because it was a manual burn, we had a three-man operation. Jack would take care of the time. He'd tell us when to light off the engine, when to stop it. Fred handled pitch maneuver, I handled the roll maneuver, and I pushed the buttons to start and stop the engine. So maybe we ought to recommend a three-man LEM after this, I don't know.
That kind of maneuver takes an immense amount of skill, and this is where the selection of test pilots for the astronaut teams became really important. Here were people who were used to jobs in which their lives depended on making very precise, good, snap decisions, controlling aircraft in often very precarious situations. And so the Apollo 13 pilots were absolutely the right people to undertake this maneuver.
Okay, stand by. 2, 1, mark it.
Ignition.
Coordinating that maneuver between the three pilots was something that had to be done right first time.
Thrust looks good. Shut down.
And it's that test pilot background that really gave them that ability.
Okay, looks good. Nice work.
Let's hope it was.
Despite being cold and tired, the three astronauts execute yet another perfect burn maneuver, correcting the flight path and the critical re-entry angle.
How's it going, Fred?
It's fine.
Just wanted to let you know that you're pretty much right in the middle of the fairway there. And well, everybody down here is 100% optimistic. Looks like we're on the upside of the whole thing now.
Okay, that sounds good.
Jim, we're ready to put that battery back on the line.
So you want us to put battery 2 back on. Is that a firm?
That's a firm.
Okay, it's coming out. Bat 2 is on the line.
Within hours of the oxygen tank rupture, Apollo 13's main power supply was dead. Without oxygen, the service module's 3 fuel cells could not generate electricity. But before the crew could evacuate to the lunar module, the command module systems started draining power from its precious re-entry batteries. This limited supply is the only power available for the capsule during re-entry.
The importance of the command module batteries is that you separate off the service module from the command module before you get to re-entry. And at that point, you lose all your power from the fuel cells. So you have to have batteries in the command module to keep you going, and the re-entry batteries do that job. And without them, you can't operate the command module through re-entry.
There was no way that the astronauts would survive if the re-entry batteries on the command module had less than full charge.
It has now been 3 days since the oxygen tank failure, and with Mission Control gearing up for the spacecraft's re-entry, their first concern is somehow recharging the command module's depleted batteries.
With no fuel cells on board to charge those batteries up, there was only one other solution, and that was to use the batteries in the lunar module to top up the batteries in the command module.
basically a trickle charge where you just keep it bleeding away while you're also using the main power of the lunar module to keep the main environment alive until you cut loose and you're just in the command module.
During preparations for Apollo 10, the mission control team had faced a training simulation, which also required the lunar module to recharge the re-entry batteries. Now, thanks to NASA's rigorous training program, ground engineers already have a proven procedure for battery charging at the ready. And having shortened the flight time earlier in the mission, there is definitely sufficient power in the command module to keep the crew alive and supply enough charge to the command module batteries.
We have a procedure which involves power transfer from the LEM to the CSM.
Okay, Houston, Aquarius, so we go for proceeding with battery charge.
Okay, go on the battery charge.
Roger.
The crew at this point has successfully completed the transfer of power from the LEM onto the command module battery charger, which is charging the 3 entry batteries to bring this from its current level of 20 amp hours up to about 40 amp hours, which would be essentially a full charge.
Our flight progressed that way down to about 5 hours prior to entry of the atmosphere. And we were just merely hanging on. We had a dead service module. We had a command module that had no power to it. We had a lunar module that was a wonderful vehicle to travel home with, but didn't have a heat shield, unfortunately, and shortly we'd have to abandon it.
In preparation for re-entry, the service module is jettisoned, giving the crew their first chance to see the extensive damage to their crippled spacecraft.
You can jettison the service module when you're ready, no big rush. Okay, sounds good.
Jim and Fred were in the LEM, and when Jim yelled fire, I jettisoned the service module. And it went off, and Jim began to pitch around to try and photograph it.
It was, to me, sort of an amazing sight.
And there's one whole side of that street missing. Is that right? Right by the high gate antenna, the whole panel is blown out. Almost from the base to the engine. Copy that.
I couldn't see exactly what was damaged. I could see material hanging out from the interior, and Fred was taking pictures and Jack was taking pictures of the service module, trying to capture some of the damage that we could see.
With the dead service module set adrift in space, Mission Control and the crew turned their attention to powering up the frozen command module capsule.
Brown, of course, was working feverishly with Jack in the command module to make a successful entry through the atmosphere.
Aquarius, Houston. Go ahead. Okay, you're go to start powering up the command module. Right-o, we're starting now.
Mission Control have developed an entirely new procedure for powering up the command module from scratch, something NASA never believed it would have to do while the capsule was in space.
The procedure in the command module was quite lengthy because we really threw away the book. We had never powered down a command module in space, and we had never reactivated one. And we wanted to get it right, and so I read back every switch and every circuit breaker.
But with an already limited power budget and time frame, this procedure is further complicated by the freezing temperatures on board the spacecraft.
They were breathing out water vapor. This was just condensing on the walls, running down the walls and windows. So there was a real concern about the moisture.
If things had not been insulated well and sealed, it would have gone into the electrics and could have caused short circuits. They probably wouldn't have got back.
The crew of Apollo 13 will now owe their lives to the lessons NASA learned from the Apollo 1 fire, when 3 astronauts were tragically killed in a test command module.
The Apollo 1 was an incredible tragedy for NASA, and obviously for the families involved. But it kind of brought NASA up to a halt. You know, it was just at the beginning of this program, and they'd lost 3 astronauts. That was a terrible shock.
The Apollo 1 fire was caused basically by bad quality workmanship in the wiring and NASA's lack of understanding of what it meant to pressurize the command module well above atmospheric pressure with pure oxygen. As soon as you do that, the flammability of materials increases tremendously and things burn so rapidly.
When a wire in one of the capsule's electrical systems arced, flammable material in the pure oxygen environment caught fire immediately, killing the crew in seconds.
So NASA learned a lot of lessons from that about switches, about wiring, about inflammable equipment.
There was a materials review all through the space program to make sure that anything in an oxygen atmosphere in a cabin was non-flammable. The funny thing is, they didn't look inside the oxygen tanks, and they were 100% oxygen with flammable materials in them, and that, of course, was one of the causes of the problems we had on Apollo 13.
But thanks to the insulation improvements made to the command module after the Apollo 1 disaster, condensed water in the Apollo 13 capsule environment would not short out any vital re-entry systems during the power-up.
I think they did an amazing job to get it powered up, considering it had been practically frozen for quite a long time.
I guess I really wasn't thinking along those lines because I knew that we were re-entering very shortly and that regardless of the damage to the heat shield, that you had to take it or not take it.
After the Apollo 13 mission, a review board was set up by NASA to investigate the cause of the oxygen tank failure. And it was eventually determined that an unlikely chain of events had resulted in a fire in oxygen tank number 2, causing it to rupture. But during the Apollo 13 mission, neither the crew or NASA had any firm ideas about what could have caused such a catastrophic system failure. Many at Mission Control had expressed their concerns about the integrity of the command module's re-entry heat shield. If there had been an explosion or meteor impact on board, shrapnel and debris may have cracked this vital protection against the intense heat of re-entry. And without an intact heat shield, the capsule and crew would burn up in the atmosphere. NASA has achieved the impossible. They have worked tirelessly and returned the stranded crew from the edge of disaster all the way back home to Earth. But Mission Control can do no more. Now all that stands between life and death for the crew is the hope that the command module's heat shield is intact.
My only thought then was, as I was sitting by myself inside the lunar module, I could see the Earth because it was the nice big triangular window. Well, Fred and Jack were powering up the command module, and even though maybe it wasn't noticeable to me, it looked like it was getting bigger and bigger and bigger. And I kept yelling back to Jack, "How are you coming? Are you doing fine? You know, when can I leave Aquarius?" Yeah.
He was a little bit nervous when he was kept asking. He kept saying, "Jack, how you coming? The Earth is getting bigger." I think he was trying to hurry me, but I don't know.
But Jack did a fine job, which was, I think, accountable for some of our good guidance into a landing. I then went from the lunar module, closed the hatch, came on down, and we jettisoned the lunar module and came on in with a spacecraft.
With just 1 hour before re-entry, the crew must abandon the lunar module, the vehicle that has acted as a lifeboat for the last 4 days, and save their lives. The trials of the Apollo 13 mission remain a testament to the flexibility and reliability of the Apollo lunar module.
Okay, you are go for fire alarm. Real fire. I'm good. Okay, copy that. Farewell, Aquarius. Okay, thank you.
This is Apollo Control Houston at 141 hours, 31 minutes into the flight. We've had lunar module jettison. Apollo 13, the age of Aquarius ended at 141 hours, 30 minutes, ground elapsed time.
Well, I'm very much disappointed, just as Fred is and Jack, that we couldn't complete the mission. Palmyra has so much to offer, we thought. We spent an awful lot of time on it. I, of course, would like to have landed on the moon, but I feel that perhaps what we got out of this flight was also well worth it.
The command module now plunges into Earth's thick atmosphere, losing radio contact with mission control. If they can survive re-entry, the astronauts will finally be home.
Apollo Control Houston, the period of blackout for the spacecraft should have begun about 20 some odd seconds ago. Apollo 13 should be coming up on max G right now. We have about 1 minute to go now from time of end to blackout. Continuing to monitor this Apollo Control Houston. Apollo 13 should be out of blackout at this time. We're standing by for any reports of acquisition.
Odyssey Houston, standing by, over. Odyssey Houston, standing by, over. Odyssey Houston, standing by, over.
Okay, go.
Roger that. Odyssey Houston, we show you on the mains. It really looks great.
Extremely loud applause as Apollo 13 on main chutes comes through loud and clear on the television display here.
Roger. Recovery on ready. Blueberry 1, Apollo 13, Apollo 13. This is recovery and your chutes look good.
The floor of the Mission Operations Control Room now crowded, and there are visible smiles on the faces of the flight controllers and astronauts in this room.
O Lord, we joyfully welcome back to Earth astronauts Lovell, Hayes, and Swigert, who, by your grace, their skill, and the skill of many men, return to us safe and whole. Amen.
I kind of think one of the most important points that can be made of this flight is the cooperation and the coordination and the initiative that people have when suddenly faced with an unusual situation that can respond to come up with the answers. And they did. They read us up procedures. Fred, Jack, and I practiced these procedures by reading them and then completed them. I think it's amazing the way that people can respond so fast to get this job done.
You know, there's a saying about a steely-eyed missile man, about people who work on rockets and spacecraft. And that accolade is only given to a very cherished few who have that quality, what you might call the right stuff. It was not until all those 3 parachutes came out and you saw splashdown that then all those emotions were released.
Personally, I regard Apollo 13 as an immensely impressive example of engineering. The systems engineering, the organizational engineering was so solid, was so intelligent, was so well structured that when the accident happened, the organization was found totally capable of dealing with it. And I think that's very impressive, and I can't imagine why anybody would want to be anything other than an engineer.
It was certainly an amazing achievement. Obviously we were really over the moon that we got them back.
I think Apollo 13 did show NASA and engineering their very best, and it's a matter of pride to have worked on the Apollo program.
Being able to take a crew of 3 astronauts in a severely wounded ship, bring it around the moon to a safe landing back on Earth using techniques which in many cases hadn't been thought of until that moment in time is a remarkable achievement. I think Apollo 13 is possibly the pinnacle of NASA's achievements in space so far.
Failure is not an option. And it was that idea that we could prevail, that we had to respect the science, the physics and the engineering, never let it get away from us, but we can do these things. It was the finest example of that spirit that's not only in NASA, it's within people, this is humans that did this. In this situation, and all similar situations, it's really about people and about what they give beyond what they're asked for.